In this series of videos, we're going to explore the properties of imaginary and complex numbers. In this lesson, we're going to go over some of the basic algebraic properties of complex numbers.
All right, hi everybody. So in a previous lesson, we introduced the imaginary number and we took a look at what it meant to be a complex number. And so what we got here was we know that we now have this variable here z, which is going to represent a complex number, and it's composed of two parts here. Okay, a real part and an imaginary part. But bear in mind here that a and b are both elements of the reals. A and b are real values, and what we do here is we multiply this part by I, and what that does is that rotates it. Okay, remember that rotates it like 90 degrees, and so then we've got this part that goes up at 90 degrees to the real number line. And then we created this complex number plane instead of a number line. It's a really neat idea here. Anyway, so now what we want to do is I should say we went back and we looked at some of the algebraic property or the operations that can act on complex numbers, and they're all basically the same operations as before. And now I just want to look at some of the algebraic properties. Now before I get into this, I'm just going to define a couple of imaginary numbers here, or complex numbers I should say. We'll let z1 here be a plus bi, and then we'll let z2 be c plus id, where we're going to let a, b, c, and d all be elements of the reals. Okay? And so now the first algebraic property that you should know is that these numbers are commutative. Or at least they obey the commutative laws for multiplication and addition. So what that means is z1 plus z2 should equal z2 plus z1. And at the same time, z1 multiplied by z2 should be the same as z2 multiplied by z1. Okay? Now, I want to spend a little bit of time here and I want to go through and I'm going to prove that this one is true. So let's take, we'll prove that these two are true here. Then I'm going to list off a few other rules and we'll kind of let those be because the proofs are going to be very similar to what I do here. So what I've got here is a plus bi plus c plus di is supposed to be the same as c plus di plus a plus bi. Well, is that true? Let's just take a quick look here. Once I drop the parentheses here, I notice that I'm going to have these two like terms. So I'm going to have a plus c plus bi plus di. And then what I'm going to do is I'm going to factor the I out of that. And that's going to look like this. It's going to be b plus d. Now, remember that a, c, b, and d, these are all elements of the reals. And so this expression right here, even is separate from the whole context that I'm looking at it in. A plus c, well, that's commutative. So I can make that the same as c plus a. B plus d. Okay, because those are real numbers, this little part right inside here, that is also commutative. So that's going to be the same as d plus b. And so now, if I redistribute that I through, okay, and then move the terms here, I can get c plus id plus a plus ib, in which case z2 plus z1 is equal to, like what we've got right here, z2 plus z1. And these are the same all the way down. So yeah, I've been able to show that z1 plus z2 is the same as z2 plus z1. Now let's take a look at multiplication. Okay, so what I want to show here is that z1 times z2 is the same as z2 multiplied by z1. And so we're going to multiply this out. So it's going to be a plus bi multiplied by c plus di. Okay, and when we multiply that out, okay, remember we're going to distribute here. So it's going to be a times c plus ADI plus BCI plus BDI squared. Okay, well, that little bit right there, okay, that's going to become subtraction. So it's going to be AC plus ADI plus BCI is going to, well, sorry, minus BD is going to equal, and I'm going to show that it's going to equal to that Z2 multiplied by Z1. Okay, and now I'm going to group together like terms, so I'm going to get AC minus BD will, plus, and I'm going to factor the I out and make that AD plus BC. Okay, now probably the easiest way to go about doing this is actually to come up here and do the same thing, just with these values in a different order. So this becomes CA plus CBI plus DAI plus DBI squared. So CA plus CBI plus DAI, and then remember that I squared is going to be subtraction. Then I'll group together the like terms. So CA minus DB, I'll factor out the I, so CB plus DA. But now remember, you can probably even see it right now. Remember that these pieces right here, okay, these are real numbers multiplied together. So I know that that's commutative. The C and the A, that's commutative. So that's the same as AC. The DB, that's going to be commutative. And then I can do the same thing not only with the multiplication but with the addition here, and I can make that AD plus BC. And again, notice that the left-hand side and the right-hand side are in fact the same. So I know that complex numbers obey the commutative laws. Now, not only that, but the complex numbers are also associative. So if I've got Z1 plus Z2 plus Z3, okay, I know that that's going to be the same as Z1 plus Z2 plus Z3, and that's basically because when I break it down into its pieces here, because the pieces are real numbers and real numbers obey the associative law under addition and multiplication and whatnot, so will complex numbers. And at the same time, I can also say that if I've got Z1 multiplied by Z2 and I multiply by a third value here, that's going to be the same as Z1 multiplied by Z2 times Z3. Okay, so it's commutative. Another rule that I can assure you that it follows is the distributive rule. Okay, or that follows the distributive law. And so what I mean here is, let's say you've got Z1, and that's being multiplied by Z2 plus Z3. Okay, well, I know that that will distribute, and I will get Z1 Z2 plus Z1 Z3. Now, we can prove those, but for the time being, we're not going to. I'll leave it up to you to take a look at those. You could define those in terms of its real and imaginary component there. Multiply those out, add them, and you'll see. Because the real number pieces are going to obey the distributive law, the associative law, commutative law, you'll see that we can make, generate a situation here where you'll see that that works for the complex numbers as well. Now what I want to do is I want to take a quick look at, a little bit more seriously at inverses and the identities here for both addition and multiplication. I think this is an important concept, and I want to make sure that this one is clear to everybody before we move on. Okay, so I'm going to break this up into two little chunks here. The first thing I want to look at is the additive identity and the additive inverse. So what I'm referring to there is, if you think back to let's talk about the real numbers. Okay, every real number, let's say x, okay, there is a number that if I add to x, it doesn't change the identity of this value. Okay, and remember, this is for real numbers here, so I'm saying that x is an element of the reals. Now, so would a here. There is a real number here, a, that is an element of the reals. Now I want you to think about it. What number is that? It probably doesn't take you very much to realize, oh, okay, you're just saying a is equal to 0. So yeah, that is what we call the additive identity. When you add 0 to a real number, it doesn't change the identity of that number. Now that also creates this idea of an inverse where let's say you've got, let's say now x and y are elements of the reals. There's a pair that exist that when I add them together, the result is the additive identity. Okay, and what that is that occurs when, for example, x is equal to negative y, when it's the negative value. So for example, 3 and negative 3, I add those together and I'm going to get 0. It's because 3 and negative 3 are additive inverses of each other. Well, we want to show that this is also true for complex numbers. So let's say that we have a complex number here. Let's say we're going to have z1 again, and this is going to be a plus bi. And then we're going to introduce a new complex number here. I'll tell you what, I'm just going to call it z without a subscript here. Okay, and let's maybe say that this is going to be x plus iy. And what I'm interested in here, this is going to be, okay, this is going to be my additive identity. And so that being the case here, when I take z1 and add z to it with no subscript, I know that my response here, my result, should be z1 if that's the case here. Now let's take a look at what that looks like. So this will be a plus bi plus x plus iy, and I know that my result here should be a plus bi. Dropping the parentheses and then grouping together the like terms, this is going to be a plus x plus, and I'm going to take the I out, and that'll be b plus y is supposed to equal a plus bi. Now, in order to finish this, what I need to do is equate the real portion of this and equate the imaginary portion of this. So this actually breaks up into two separate equations. I've got a plus x from the left-hand side. That has to just equal the a on the right-hand side. While at the same time, b plus y on the left-hand side, multiplied by the I, must be equal to just the b there. Now, in order for this to work here, remembering that a, x, and b and y here are all supposed to be real numbers, well then I can tell you that x is 0 and y is 0. So therefore, z must be this number 0 plus I times 0. And this is the additive identity. Okay? Now, that being said, we should be able to identify the additive inverse. Okay? So now let's say we've got two numbers here. So we've got, again, we're going to have z1, and this is going to equal a plus ib. And then let's say we're going to have z2 here. And again, I'll go for x, well, I'll go for c and d this time. So c plus id. I want to find out what this looks like if it's the additive inverse of this one. Okay, so this is going to be the additive, whoops. Additive, oh boy, I really did a number on that one. Additive, whatever. I had it right there. Additive inverse, okay, of Z1, which means if I add those two together, Z1 plus Z2, my answer should be 0, okay, or 0 plus I multiplied by 0. So this is going to be A plus IB plus C plus ID is going to equal 0 plus I times 0. So this is A plus C plus I times B plus D equals 0 plus I times 0. And now once again I have to equate the real part and equate the imaginary part. So A plus C has got to equal 0, but also B plus D has got to equal 0. And what that means to me is that C must equal negative A and D must equal negative B. That's how we create the additive inverse. Okay, so therefore I know that Z2, the additive inverse, must be negative A minus I times B. And there you go. Now, the fact that that exists is actually kind of useful because it helps me define subtraction. Okay, because therefore now what I can say is that if I've got Z1 minus Z2, let's say, another way I can think of that is Z1 plus the additive inverse of Z2. This just gives me another way of handling that specific kind of problem. Now let's look at multiplication. Okay, so now we want to take a look at the multiplicative identity and the multiplicative inverse. So what we mean by multiplicative identity here is that there's a number. Okay, let's say you've got x and a, and they're both element of the reals. There is a number out there that if I take x and multiply it by a, I still get x. And again, it probably doesn't take you long to realize, okay, a is just equal to 1. So when I multiply by 1, okay, whatever I'm multiplying by gets to maintain its identity. It doesn't change. Okay, so what we want to do here is we want to see, is that also true for complex numbers? So let's start with my Z1, and again I'm going to go back to a plus ib. And let's say I've got this other one here, z, and let's just call it again x plus iy. And I'm going to let this one here be my multiplicative identity. Okay, so what I know is that if I multiply these two together, if I multiply z1 by z, I should be getting z1 as a result. Now, let's take a look at what happens here and see if we can figure out what's going on with just z here, the multiplicative identity. So it's going to be a plus ib multiplied by, what do I have here? X plus iy. And I'm suggesting that that should be equal to a plus ib. Okay, so let's multiply that out. So it's going to be ax plus iay plus ibx, okay, plus I squared by. Now, I know, I'm going to put these things together. I know that's going to become -1, so it's going to be ax minus by, and I'll factor the I out of those two, so I'll get ay plus bx is equal to a plus ib. Now, when I set the real parts and the imaginary parts together, I get ax minus by should be equal to a. And I get ay plus bx should be equal to b. Well, okay, well, it doesn't take much fiddling to realize that, look, what's got to happen here is that y has to equal 0 and x has to equal 1. And if I look over here, y is 0, x equal, that's exactly what's going on here. So as long as x is equal to 1 and y is equal to 0, that works. So therefore, my multiplicative identity is going to be 1 plus I times 0. Okay, basically just the real number 1. That works as the multiplicative identity for complex numbers. Now, that being said, there should be a multiplicative inverse of a number. So what that means is, if I've got, let's say, two real numbers here, so again, we're going to start with x and a, and we're going to say that they're elements of the reals. I know that if x multiplied by a is equal to 1, the multiplicative identity, then let's say here a must equal 1 divided by x. There is a real number that exists such that when I multiply those two together, I get 1. Now, with the exception of 0. 0 doesn't have that, okay? And that's okay. There's just one little exception there. Now, let's take a look here and see what that looks like when it comes to complex numbers. So, again, I'm going to start with my a plus ib, and I'm going to create this other value here. I'll make that c plus di. And what I want to happen here is when these two are multiplied together, I want the result to be equal to a plus ib. I want this to be my multiplicative inverse, okay, of Z1. So I know that if I've got Z1 multiplied by Z2, the answer should be 1 plus I0, should be the multiplicative identity. Okay, so this is going to be a plus ib multiplied by c plus di, and that should equal 1 plus I times 0. So now I'm going to expand that out. So ac plus iad plus ibc plus I squared BD is going to equal 1 plus I times 0. And again, that I squared will become negative 1, so I'm going to get AC minus BD plus I times AD plus BC has got to equal 1 plus I times 0. Okay, well this is going to be a little bit more complicated than the other ones here, but what I know here is AC minus BD must equal 1, and AD plus BC has to equal 0. Okay, now I'm gonna flip this over so that we'll start fresh here. So again, what I said here was AC, oh no, see now I'm forgetting. AC minus BD was equal to 1, and then AD plus BC was equal to 0. Now, what I want to do is I want to figure out what my values are for D and C. Well, I've got a system of equations here that I can solve. So let's just take a quick look here. What I would like to get rid of, let's say, is I'd like to get the D by itself. So maybe what I want to do is I want to get rid of the terms here with the C's in them. So I'm going to multiply this equation through by B. So this will become ABC minus B squared D equals B. And I'm going to multiply this equation through here. So that this is like my equation 1. Here's my equation 2. And so I did B times equation 1. And I'm going to multiply equation 2 here by, I'm just going to get by A. So A times equation 2. So that will be A squared D plus ABC is going to equal, well, 0, because I multiply that through. And now to get rid of those terms, I will subtract those two. So ABC minus ABC goes to 0. I'm going to get negative B squared D minus A squared D is going to equal B. Factor out the D. And I'll get negative, and I'll put this in an order that looks better. And then I'm going to divide, take out the negative and move it up here, and I'm going to get negative B over A squared plus B squared. Oh, okay, so now I've got a value for D that's in terms of A and B. Now I want to do the same thing. This time what I want to get rid of is the other term. So let's get rid of the AD term. So I'm going to multiply the first equation, this case by A, and that's going to get me, my first equation is going to get me A squared C minus ABD equals A. And I'll multiply the second equation through by B. So ABD plus B squared C is equal to 0. And because I want these two terms to cancel, I'm going to add them together. And I'll get A squared C plus B squared C is equal to A. Factor out the C, and I get A over A squared plus B squared. And there you have it. Now I know that was a whole lot, and I kind of went through that relatively quickly. I kind of have to assume at this point that if you're looking at a video like this, you've already seen systems of equations, that I'm not really doing anything here that's new. So therefore my Z2, my multiplicative identity, is going to be A over A squared plus B squared minus BI over A squared plus B squared. And that's the multiplicative identity, the multiplicative inverse of a regular value here. Now, at this point, of all the stuff that I've done today with this video here, this is probably the one bit that maybe immediately off the top here, you're not 100% sure that that's actually going to work. So let's take a quick look at an example here. Let's say that Z is equal to, let's just make it easy, 2 plus 3i. Okay? Now, what I want to do is I want to come up with a multiplicative inverse and just check to see that it actually works. So if that's true, and let's call this Z1 here, then Z2, my multiplicative inverse, is going to be A, 2, over 2 squared plus 3 squared, okay, minus B over 2 squared plus 3 squared. And so that's going to be 2 over, well, 2 squared is going to be 4 plus, so it's going to be 13 minus 3I over 13. So if this is the number that I start with, this is apparently supposed to be my multiplicative inverse, which means if I multiply those two together, I should be getting a 1. Now let's just double check that. So 2 plus 3I multiplied by 2 over 13 minus 3I over 13. Okay, so that's going to be 4 over 13 minus 6I over 13 plus 6I over 13. Well, oh, I like that. That's going to go to 0. And then I'm going to have this negative 9I squared over 13. Well, that's going to be 4 over 13. These terms are going to cancel inside the middle here. That I squared is going to become negative, so it's going to make that positive. So plus 9 over 13. And 13 over 13 is equal to 1. And so there you have it. So there it is. That is the multiplicative inverse. Now, the reason why that might be considered really, really useful to us is because of what it implies about what we can do with these values here. Okay? And so what it implies here, okay, is that if Z1 multiplied by Z2 is equal to 0, then I know that at least one of Z1 or Z2 is 0. That has to be true. Okay? Now, I'm going to show that to you right now, and then that's just kind of where we're going to leave it off with this particular lesson here. Actually, that's not true. I'm going to show you one more little thing after we go through that, but here we go here. So let's assume, okay, Z1 times Z2 is equal to 0. Just assume that that's true. Now we're going to take a look at these inverses here. Oh, and by the way, I'm sorry, I should have gone up here and shown you this here. Because we know that this is true, one of the ways that we would write this, and I should have done this as soon as I said that, is we'll use that little to the negative 1 to indicate that this is the inverse, okay, the multiplicative inverse of Z1. With the additive inverse, we put a negative out front. With the multiplication, we're going to put this, raise it to the negative 1 power here. Because the reason I bring that up is because I'm going to use that notation right away here. So let's just assume here that that we're going to show that let's say Z2 is equal to 0. So I want to show that Z2 is equal to 0 by first of all saying that I know that Z2 is going to equal 1 multiplied by Z2. Now, because I know that a multiplicative inverse exists for Z1, because I just showed that it exists for all numbers, as long as both its pieces aren't equal to 0, okay, because there is no multiplicative inverse of 0 there, then this is going to be Z1 multiplied by Z1 inverse. I know that when I multiply those two together, I'm going to get 1. That's multiplied by Z2. I know that multiplication is commutative. I know that multiplication is associative. And I also know, based on my assumption up above here, that this is equal to 0, which means this is going to be Z1 inverse multiplied by 0, which has got to equal 0. And so there you have it. If we know that Z1 multiplied by Z2 is equal to 0, then I can show that one of them, and I could very easily have swapped the 1 and the 2 here and gone through the whole thing, one of them has to be equal to 0. Makes it easy to solve equations. Okay, I want to do one last thing with you, and I just want to illustrate that these two expressions are the same here. So 1 divided by Z1 is going to equal the multiplicative inverse of Z1. Okay, Z1 to the negative 1 here. So let's pick a Z1. Let's make it, I don't know, let's make it 2 plus I. just for easy math here. So we're going to let A equal 2 and B is equal to 1. Now, we looked at, in the previous lesson here, we looked at how you do division here. So if I've got 1 over Z1, that is going to be the same as 1 over 2 plus I. And I had suggested to you that the way you do this is to multiply numerator and denominator by the binomial conjugate of the denominator. Okay? And so that's going to get you 2 minus I in the numerator. And when you expand that out, I'm going to get 2 squared. I know that the middle terms are going to cancel when I multiply that out. That's going to be minus I squared. So that's going to be 2 minus I in the numerator, and this will be 4 plus 1. And so this will end up being 2 minus I, whoops, I'm going off the screen, 2 minus I over 5, which becomes 2/5 minus I over 5. Now, what I want to show you here is that based on our own definition, okay, that our inverse, add a multiplicative inverse, is going to be the same thing. So let's go over here and take a look at Z1 to the negative 1 here. I know, based on my own definition here, that that is going to end up being 2 over 2 squared plus 1 squared minus 1I over 2 squared plus 1 squared. This is just me following the formula that I established a few moments ago. And so that's going to be 2 over 4 plus 1 minus I over 4 plus 1. And then there it is, 2/5 minus I over 5. And there you can see they're exactly the same thing. Okay, so therefore you can conclude, okay, that 1 over Z is the same as that definition that we came up with for the multiplicative inverse of Z.